This is the technology section. We're going to use the same concepts as the non-technology section, but of course this time we need to use the graphing calculator in order to find our answers. In number one, it gives us the derivative, f prime of x, and we're going to be asked questions about the function f, the function that we do not have, the function that we cannot see. So we have to use purely concepts in order to answer these questions. Okay, so f prime equals the function that you see there, and that's defined on the open interval -2 to 2. So because we're using the first derivative test, I want to get a graph of the first derivative. So you might want to take a moment to type that into your calculator. And what I'm going to do here is reproduce the picture of the graph. Now we want to graph this on the domain -2 to 2. So 1, 2, and -1, -2. Okay, so once you have that in your calculator and graph it, the function should look something like this. A crude sketch of it, but please remember what you just graphed was the function f prime of x and not the function that we're answering questions about. So the next thing we want to do is we want to find horizontal tangents by finding where the derivative equals 0. So you'll take a moment and find those and say that f prime of x equals 0 at, and you should have found -1.299 rounding to 3 decimal places, and x equals 1.552. In question part A, they want to know where the function f that we can't see has a relative max. I could actually start off and say f has a local or relative max at x equals, and let's say I don't know for a minute, so I'll put an underline, but I do know the reason that we learned. It's because f prime of x goes from positive to negative at this x value. So we come over to the graph, and the derivative, when it's positive, means the graph will be above the axis, and when the derivative is negative, the graph of the derivative will be below the x-axis. So you can see here at this point the derivative went from positive to negative. So at x equals 1.552, because our f prime of x went from positive to negative, at that x equals 1.552. Please remember that it's not just enough to say what we said here in part A. We also needed to state this somewhere on the paper in order for the first derivative test to be employed properly. Okay, so now we're going to look at B, and B says on what interval is f decreasing. My reason will be because f prime of x is less than 0 on some interval. So you can see where the derivative is below the x-axis. So we're going to say f is decreasing on, I'll use a -2 in parentheses, -2 is not in the domain, to the -1.299 bracket, union bracket, 1.552, all the way to 2, but 2 is not in the domain, so we get a parenthesis. Because f prime of x is less than 0 on -2 to -1.299 in union with 1.552 to 2. Number 2 here, f prime of x equals the cosine of x cubed. Please make sure that you are in radians. I'm going to find horizontal tangents by saying f prime of x equals 0 at, so this requires the graph, and so I'm just going to take the time to actually draw this graph, and that's going to be on the domain of 0 to 2. So when I graph this function, this derivative it's going to come in and do one of these guys. Come down, up, crossing the x-axis at 3 locations. And those are the 3 locations I'm supposed to find. Use your calculator to find those, and f prime of x equals 0 at x equals the smallest of them, 1.162, x equals 1.677, and x equals 1.988. Okay, so we are ready to answer the questions. Question A wants to know where the local minimums. So f has a local minimum at x equals blank because f prime of x goes from negative to positive at x equals blank. So let's look at our graph. Again, this is f prime greater than 0. Below is f prime less than 0. And where will the derivative go from negative to positive? From negative to positive here. And that's going to be x equals 1.677 because f prime goes from negative to positive at this x value. Perhaps you can look at this and think of it like the no point number line, where you have a 0 here, a 0 here, a 0 here, and this being the x-axis, and then you determine the sign of the derivative. So it's above, so it's positive, then it's below, so it's negative, then positive again, and then negative again. Perhaps you'd like to construct that, but it's a no point number line, so you won't earn points for it. For part B, on what interval is f decreasing? F is decreasing on, let's see, bracket 1.162 to 1.677 in union with 1.988 to 2. Now the 2 is the only value not in the domain. And that again is because f prime of x is less than 0 on the parenthesis version of the interval as shown here. The final example here, example 3, is a little tricky. One of the tricky things about it is just getting the zeros. So here is a picture of the graph, and I'm going to graph it on the domain 1, 2, 3. So you really got to be careful. It's hard to see this on the calculator, but it does dip below. When you graph this, it's going to look like most of it's above the x-axis. See, I know that there's a sliver of it below the x-axis because of this negative 1/10. Now, in order to find the 0 on the calculator, we have to be a little bit careful. So when we have our cursor and we're moving to the left, what happens is, because of resolution issues, it's jumping off the graph and then it's not defined there, and it may give you some troubles. So when this asks you for the lower bound, instead of scrolling to the left to find that lower bound, you can actually just type in the value of 0, and if you type in 0, it's going to give you the lower bound. Then you can use your arrow to scroll to the right to give you the upper bound. Let's not forget that this is a picture of the derivative, like it has been in the other 2 examples. And when you find that 0, so let's just say that f prime of x equals 0 at x equals 0.010. That's correct to 3 decimal places. Okay. Now we're going to say here for part A that, what does it want? Local minimums. F has a local minimum at x equals 0.010 because f prime of x goes from negative to positive at x equals 0.010. I think you're getting the point now. For part B, f is increasing on bracket 0.010 to 3. Now I'm including the 3 because that's in the domain, and that's because f prime of x is greater than 0 on the parenthesis version. Okay, now why this example? Well, one is to help illustrate how to get the lower bound when you're running off the calculator screen. But the other is we have to be a little bit careful here because I have endpoints, and automatically endpoints are candidates for being a local min or local max. So the question I have for you, we're going to look at those endpoints. So for you, what do you think here? F of 0 is a local max, or is it a local minimum? So again, we can't see the function, but if I could, would there be a local max at x equals 0, or would there be a local min? Same with the other side. F of 3 is a local max or local min. You might be surprised by this, but at each endpoint we have a maximum. Let me explain here. So I'm going to draw the no point number line, and we have a 0 way over here at 0.010. And we can see that the derivative was negative, but then the derivative went from positive. So the derivative negative means that the function's decreasing. So if I start, if this is f of 0, I don't know what the number is, but let's say that's f of 0. The first thing the function does is decrease. So it has to decrease from somewhere. It's decreasing from a local max. And then we hit our local minimum as described in part A, and then it does what? It increases up to somewhere. It increases up to the maximum. Most people know that there will be a max here, but a lot of people, because they see it under the axis, assume that that's going to be a minimum, forgetting that this is the derivative and that it has to decrease away from something. So local max and a local max. This is called an endpoint analysis, and the AP people will not ask for this endpoint analysis. They would have worded the question from 0 to 3, but I'll put on an exam, a little section similar to this, where I ask you to analyze the endpoints.